Okay, in this video, I will show the equations, I will explain the equations of our inverted pendulum, inverted simple pendulum. An inverted pendulum mounted on a cart is shown in this figure here. So you can see that this is the cart, and on this cart we have this rod. Rod is mounted, and it can the rod can rotate, okay, around this point here, P. Okay, so when you apply force U, U here, this U is the force applied to this card. So maybe by applying some force here, you will be able to make this angle, the angle of theta, which is the angle between the vertical axis and the rod that is mounted here. You want in general, we assume that the control problem here is to make this angle zero. Okay, what it means that you are stabilizing the inverted pendulum. So we will assume that capital M is the mass of the card. We will assume that L is half the length of this rod. Okay, and now we will assume that you will see that the rod, the center of gravity of this rod here is in the middle of this rod like this. So it's at the distance L with respect to point P. Okay. So assume that our control objective is to keep the pendulum in vertical position. However, you can see that the system is unstable because it may fall over any time in any direction unless uh, a suitable force U is applied on the card. Here we consider that the pendulum, the rod, moves only in two dimensions. Okay, it can move only in two dimensions, so we only need the angle theta to determine the position of this rod. Assume also that the center of gravity of the rod is at its geometric center. We denote capital M, the mass of the card, and uh, M, the mass of the rod. So we define the angle of the rod from the vertical lines at theta, and it's positive to the right. And we define the coordinates of the center of gravity of pendulum as x, g, and y, g. And it's easy to see that this is the relationship between these coordinates of the center of gravity of the rod with respect to x, where x is the position of the center of gravity of the car. Okay, so let's try to understand what are the forces that are acting on the road and that are acting on this cart. Okay, so first, as I told you, this U here is the force that is being applied on this mass. And the other force that is being applied on this mass is the force applied by the rod on the mass. Okay, on the cart, and that is equal but opposite to the force that is applying this cart on the road. We have seen this several times. So denote F, the force applied on the road by the cart. Okay, this is the force applied by the cart. So the horizontal motion of the center of gravity of the pendulum rod can be described by, so here we have in the horizontal axis, uh, we have, this is m, this is the mass of the rod, and this is in the vertical axis. So this is the Fx, is the projection of force F on the horizontal axis, and this is Fy, is the projection of force F on the vertical axis. So, and you see that in the vertical axis, we only have this force and mg. Mg is the weight of the rod, okay, applied to the rod. So here we have a more complex type of motion, because note that in this system, the cart is moving only in the horizontal axis, so it's only translational system. But if you see this, what is happening is that the center of gravity of the rod is moving also. It's moving uh, in two axes, okay, in the horizontal and vertical axis, and the rod itself is rotating. It's rotating, okay, around the axis that is in its center of gravity of the rod. So we need to write not only this equation here for the rod, but also we need to write this differential equation here, in which we have this j, where j is the moment of inertia of the rod, and this is the angular acceleration, and these are the projection, the torque is, in fact, torque applied to the rod as a result of force of these two components of force F, Fy and Fx. Okay, and finally, we cannot forget that we also need to write this differential equation here for the cart. In the cart, we can say that because the cart is moving only in the horizontal axis, we only need this differential equations, only one m, capital M, for into this acceleration equal to u, this is the external force, and minus Fx. So if we assume that the angle theta is small, we can assume that the sine of theta is almost equal to theta, and the cos of theta is almost equal to 1. In that case, we can write this approximation here for the coordinates of the center of gravity of rod, okay, and then we will obtain, if you use this approximation and you replace this relationship here in the previous equations, the four equations that we have seen, finally you can replace all these equations only by two, that are these two equations that we have here. This one is involving x, theta, and the input, and then here we have x also, and then theta and theta in this side. So finally, you can see that if you, because now this is, of course, this is just one approximation that you are, because here you are assuming that the angle theta is small, and but if besides we assume null initial conditions, so initially the pendulum is in its equilibrium position, so we can write these two equations now in terms of the Laplace variable s. And once you do this, you can write the transfer function, okay, taking as output variable the angle of your inverted pendulum, and the input will be the force which is applied to the card. Okay, so and you can see that you obtain this expression for this transfer function. That you can see that in fact what will happen is that in this case you will see that the well, if you can also uh, neglect, because usually this j, that is j is the moment of inertia of of the road. If j can be also neglected, in that case you can say that okay, so you only have this relationship here, and what happened is that this is a unstable system, which means that it is very difficult to uh, find or to apply, to know what type of force you have to apply in order for this system to remain stable. This is why the inverted pendulum, in fact, is the perfect example that you always need some type of control system in order for this inverted pendulum to remain vertical. Otherwise, it will be very difficult and the pendulum will fall in as any of the two directions, to the left or to the right. Okay, so in the next videos, I will show you how we can use other type of tools in order to simulate the time response of linear, any type of mostly linear systems, because we will consider only linear or linearized systems. And so, in fact, if you want to understand what is the relationship of this system with the bicycle model, in fact, we will see in the next video that the equation describing the roll angle of the back frame of my bicycle, it's very similar to the inverted pendulum model that we have seen in this video. Okay.